Hello, physical science students. This is Mr. Kraft coming to you from my room over at Cal. We've been talking the last couple of video lectures about simple machines. And we said that what these do is they make work more efficient. And we further went on to say what that basically means is they allow us to do things and waste less energy in doing so. And we said the three basic types of simple machines are the lever, the wheel and axle, and the inclined plane. Now, the wheel was the last of these for humans to discover or to invent. Probably about the end of the Stone Age, beginning of the Bronze Age, somewhere along that line. Probably the Bronze Age actually. It revolutionized human culture by making possible chariots, carts, everything else. The inclined plane probably wasn't even invented, because if you think about it, a hill is just a natural inclined plane. So all humans had to do when you walk up a hill is somebody gets the idea, well, okay, if you want to get something up to this ledge, we'll just stick a board across it, and it's just like going up a hill. So probably the first simple machine to actually be invented, as opposed to just figured out, probably the lever. The person whom we associate the most with levers is the great Greek philosopher and mathematician and scientist and engineer. He was a busy guy, Archimedes, who lived in Sicily, in the city of Syracuse, round about 300s BC, so about 2,300 years ago, give or take. Archimedes was the first man to calculate pi to about 3 or 4 significant digits. He devised all kinds of inventions, including possibly reflecting mirrors that burn ships, flamethrowers, the so-called screw of Archimedes, which was to get water out of rivers. He did all kinds of things. But for our purposes here, he was one of the first persons to understand how levers actually work. And one of his most famous statements was, "Give me a place to stand and I will move the earth." You can see he was not really known for modesty, but he was a pretty brilliant man, so I guess you kind of cut him some slack on that. In case you wanted to know, if we imagine a very, 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 very long lever, and we imagine Earth on that lever, just to make things fun. As you may or may not know, the ancient Greeks, by the time of Archimedes, were quite aware that the earth was spherical. Put a nice little Greek robe on, so he's not just any stick figure. Give him a beard and long Greek hair. So if you actually could put Earth on a lever and have a great big long surface to sit on, so of course this would not be possible in reality, but just for kicks, if it were, how long would the lever have to be? Now, I'm not going to go into all the math of this for what I'm telling you here, but suffice it to say, it would be 6.25 times 10 to the 19th power, which would be equivalent to 62 quintillion $500 quadrillion miles. 62 quintillion 500 quadrillion miles, which, to give you some idea of how far out that is, the man-made object that is farthest away from us. So here's the sun, and then you have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. They don't count it as a planet anymore, but Pluto. Way, 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 way out here. If you drew the whole solar system like that, here's the sun, and here's Pluto. Voyager is out here about 14 billion miles away from us. Well, we just now said Archimedes would need a 6.25 quintillion mile lever, or 62 quintillion 500 quadrillion, if you want to put it that way. That would be about a billion times as far as the Voyager probe is from us. And it's out of our solar system now, actually. So that would be an awful long lever. But that could not actually happen in reality, but it's kind of an interesting concept. So anyway, what I want to do is to talk about the 3 different classes of lever, is what they call it. There are 3 classes of lever. And the basic parts of a lever are what we use to define the class. So here's a rock, or maybe earth. And here's a person lifting the rock, or maybe it's Archimedes lifting the earth. You have the force that the person is producing. He's pulling the lever downward. He or she is pulling the lever downward. You have the load, which, is the load. It's what he's trying to lift up. And then the pivot point, which, as I've mentioned previously, we call the fulcrum. And the three classes of lever are defined in terms of where the load and the fulcrum and the force are with respect to each other. And here's a good diagram to show it. First class lever. Now, in this case, when we say first class, it's not like it's better than all the other levers, but it is probably the one we think of first. It's the simplest one. You have the effort or force and the resistance or load, and the fulcrum is between them. The fulcrum is between the effort and the load. And this is what I drew here on the whiteboard. The fulcrum is between the force or effort and the load. They're between each other. It's between those two. So the force goes down, the load goes up. A second class lever, the load is between the effort and the fulcrum. So the effort or the force and the fulcrum are on opposite ends. And the best example, if any of you have ever used a wheelbarrow, where you're kind of lifting up, the effort goes up, the load is actually going downward. Because to demonstrate that, you start with a wheelbarrow. And here's a load of, say, sand or concrete or whatever in it. Basically, the wheel serves as a fulcrum. So then you apply effort. You lift up the handles. Kind of pivots on the fulcrum. The force is going up on this handle and the weight is going down. Then that allows you to easily push it forward. So the load goes down, the effort goes up. The last kind of lever is a third class lever. The load is at one end. Second class, the effort and the fulcrum were at opposite ends. Here, the resistance and the fulcrum are at opposite ends. And the effort goes between them. And a steam shovel is the example they use for that. The effort is right in here in the middle. And I can't really think of a good example off the top of my head of something you'd be doing this where you might actually, actually a regular shovel would probably exemplify that. Because, okay, so here's a shovel. That's a poorly drawn shovel. I went back too far. So here's a shovel. Here the handle goes out. And usually you're going to have one hand holding at the very end and another hand holding here. And you put the load on the shovel, you're shoveling some dirt, your back hand is going to be the fulcrum. The forward-facing hand is going to give you your effort, and your load is going to go in the same direction as the effort, just like we see here. So the motion is right beside the load going up, and the effort's going up, and the fulcrum's on the end. And if you have ever shoveled anything, you know how that is actually what happens, not just with a steam shovel, but also with a human body shovel, the ordinary kind we use there. Your backhand, whichever it is, if you're left-handed, you hold it just the opposite way. If you're right-handed, you hold it differently, but it works the same. The rear hand is the fulcrum that it pivots around. Basically, it's going in a circle around that. Your forward hand is providing most of the effort, and the load is going up on that end. Okay. So I'm going to go over here to this picture one more time. You could probably do a screen capture of this and download it for your reference if you want to, but I'm going to see if I can do that and put it on the Google Classroom for this class, so you'd be able to get to it there. I'll do that a little bit later. For right now, that's all I want to talk, so I want you to understand the different classes of lever and examples of each. Okay. The work for this topic for the last couple of videos and this one will be in the Google Classroom. And of course, if you have any questions, feel free to contact me. I'll give you details about this next week. We'll probably be doing some Google Meets. For now, that's all. And I hope you're having a good day, a good week. Hope all is going well for you. And I'll talk to you the next time. Goodbye.